Video now is going to be on simulating a pure birth process in Excel. So you can see here I've got an Excel spreadsheet. This is similar to our queuing model. I've got a random variable for each step, just equals rand. And I've got my B and my delta T here defined. So B is a growth rate of 3%. Delta T is 0.1, so we're doing a time step of 0.1 years, whatever you want your units to be. Okay? And so I'm starting with a population of 100. We don't have to start with a population of 1 with a pure birth process. You can start kind of wherever you want. You do need to make sure that whatever population you end up with, delta T needs to be small enough that the population times B times the delta T stays less than 1. Okay? And that's because if you make B too large, so let's see, 100 times F1 times F2. So population, starting population times B times delta T. In this case, is just 0.3. So we've got a 30% chance of having a birth in any unit delta T. If we make this larger, though, say we take B up to like 0.7, then B times delta T becomes 7, a probability of 7 of having a birth each time, which is greater than 1. And so what you see is that then we just get a birth every single time. And so we've overwhelmed our system. So the idea is if you want a birth rate of 0.7, you need to reduce your delta T small enough so that it stays below B times the population times delta T stays less than 1. And in fact, it needs to stay that way. So you can see here eventually we get to a point where population gets large enough that we're having a birth every single unit of time. So 0.01 isn't even small enough for 0.7. If we want to do 0.7, we need to do 0.001 or something even smaller to make sure that that stays low, so that we're not getting a birth every single unit of time. Okay? So our population calculation here, what we do is we just do B2, so the previous population, plus if our random variable is less than the previous population, times B times delta T, right? Remember that was our probability we moved to the next state. We add 1, otherwise we add 0. Okay? And so that's kind of the mechanic for checking to see and doing the simulation. And so you can see here where C4 is very small, and so that's less than B times delta T. And so we add another member of our population. Similarly, C14 is small, and so we get another population member, and so on and so forth. Okay? And so if you graph this, so now we've got it over a very short period of time. So 200 data points only gets us to 0.2 now, and a population of 112. But if you graph this, do a scatter plot, what you'll see, so this looks kind of choppy, but you get something that's roughly like exponential growth. Let me switch back to 0.03 and 0.1. Okay, so this is a little bit smoother because we're actually getting some growth over the whole time. And so you get something roughly akin to exponential growth. And so if you remember, the deterministic model for population growth would be 100, our initial population, times 1 plus B plus our rate of population growth to the T power. And so if you look at that, I've got that in here as deterministic. So 100 times 1.03. I guess I should really have that written out in formulas. Let's do 100. So let's make this actually right. So B2, our initial population, times 1 plus our F1, our B to the A3. That's actually what this should say, rather than hard coding things in. So let me fill that down. And so what you see is that you get population numbers up here that are very similar to what you get from the stochastic model. And that's not an accident, right? So if you graph all of this together, so that's our continuous and our discrete deterministic model, or deterministic model rather, and insert scatter plots. What you get is you've got your continuous deterministic model, your continuous stochastic model in blue. You can see the blue does go a little bit higher, but they're very, very similar. They track. And that's because the stochastic model, the expected value of it is actually going to be the deterministic model at any point. So it does track what we expect ends up happening out. This grows roughly exponentially. Okay? So that's the end of the lecture. We'll talk some about this in class.